Hey everyone, my name is Phil. I'm an alchemist and I work with antimatter right here at the Martinos. So if you can't hear me, let me know. Normally I can get pretty loud. I need my notes for this a little bit and I didn't get it all memorized. But what we're going to talk about today is how we're going to do alchemy. That's going to take up about 6 minutes or so. And then why the Martino Center has a Philosopher's Stone in the first place. And then lastly, a little bit about the development of this. So real quick, what an alchemy overview is, and this gets a little technical, so just bear with me as much as you can. We take one element and we turn it into a different element. Because otherwise it's just chemistry, so we're doing alchemy here. Oh, sorry. So what we're going to do this with is a cyclotron, a linear accelerator, a synchrotron, which is just a bunch of linear accelerators in a circle, or even a cyclotron that feeds a linear accelerator. The whole Large Hadron Collider, that's just a bunch of synchrotrons feeding themselves. So where did we get this technology, along with the joke that I just gave away? Not aliens. This is gonna maybe sound crazy, but like when we go through this whole thing, I promise, like every part of a cyclotron, it's really, really easy to understand and it's not complicated. So what this is this is a TIG welder, and this is the arc that the TIG is generating. So what we're gonna do with this is very similar to our ion source, is we're gonna have an electric arc, and then we're gonna pass hydrogen over this arc. What this is going to do is generate plasma, that fourth state of matter. So we're going to have a proton with 2 electrons, because when we separate the hydrogen. So right about now you're thinking, wait a minute, hydrogen plus electricity equals Hindenburg. It could equal the Hindenburg, but you need the atmospheric oxygen. Because otherwise, not so much. So what we're going to do is this is a bunch of, and this is the busiest slide up here, I promise. This is a bunch of TIG welding, images of the arc with different shielding gases, whether you can use argon or helium, and how it will actually affect the arc stability. Well, what we're going to do is we're going to use the shielding gas of argon. The tank's going to be right about neutral pressure. We're going to pipe in a little bit of extra argon to keep the oxygen, the atmospheric oxygen, out of the tank. So when we keep the oxygen out of the tank, what this is going to do is, okay, so bear with me here. Have you ever been driving and you put your arm out the window going like 60 miles an hour and you can feel the air? Or if you've ever seen like the space shuttle as it comes down and it's generating all that plasma and all that ionization? We have to get all that air, which when you start to think about how fast we're accelerating these particles, these protons, around about 15% the speed of light. So we have to get that out. And our ion source is actually right about as complicated as a light bulb. This is an HID light bulb, high intensity discharge. Have you ever seen those cars that are really annoying that have those super bright headlights? This is what's blinding you. So what happens is the electric arc actually passes right here to right here, and that electric arc is very bright. But so the issue now is we're putting hydrogen into the system. So inside of this light bulb, they have a vacuum. So how we do this, and it's really, really complicated-ish, is what we're going to do to get rid of the extra hydrogen that doesn't turn into plasma that we're not going to accelerate, is we take an air compressor and we hook it up backwards. Because if you hook it up backwards, you're going to make everything in the tank actually lower pressure. And that's what we're doing. That's how we're going to get, 1, the atmosphere out, and 2, the oxygen out. Now, the other 2 systems I'm going to talk about, this is a tough group to impress, because the first one is a magnet, like in an MRI machine. A little bit different than the MRI machine. Our magnet is much, much less powerful. The magnet that we use is basically just and only a magnetic bottle. It holds these protons with 2 electrons, which are very reactive. in the right place. For the next system, an RF, radio frequency modulation. But when you start thinking about what type of systems that this RF has, this is way too complicated. So let's bring this down a little bit in the complication level. Yes, these have RF systems, but again, way too complicated. We need a little bit less. You know, there's more colors, but still too complicated. Let's come up with the right level of complication for an RF system on a cyclotron. Yeah. We have a really, really big microwave that's accelerating these protons. The magnet that's keeping them in the right order, they're going to get up to about 15% the speed of light. So we have to get the protons that we're accelerating out of the cyclotron. So, and this is the only like slide specific thing here. We have the negative proton because it has 2 electrons. It's going to go through the carbon stripper foil, and then because its charge is reversed and the magnetic field stays the same, it's going to leave the tank. So the target, we basically just put it in the way of where the proton was going to go anyway. Sometimes on cyclotrons we'll have Halbach arrays or compensator coils, but with our cyclotron we just put the target where it was going to get in the way. This is what our cyclotron looks like. This is actually what we have right over by bay 6 and bay 7. The shield, which is this thing, is out. Normally it goes in. This is what the cyclotron looks like without shielding. This right here is our air compressor hooked up backwards. This is the target system. This is the antenna for the radio frequency, and the ion source is right up here. So why do we have a cyclotron at all at the Martinos Center? Well, I can answer this with just one word: radioactive cyanide. Because I mean, who doesn't want radioactive cyanide? So aside from radioactive cyanide, which is my favorite thing, we make radiopharmaceuticals. So when you think of all your medical imaging things, you have your PET scan or your CAT scans, your CTs, your MRIs, a little bit of ultrasound. These give you very, very good anatomy images. What nuclear medicine does is it gives you physiology images. You're either going to measure metabolism, receptors, receptor bindings, things of that nature. This is what nuclear medicine looks like. If you know what the thing is on the right, just hold on for a second, but this is about as accurate as we can get with bone scans. But what we're measuring here is the metabolism of the bone. We're not measuring where the bones are. This thing on the right, believe it or not, it's a heart. That's what cardiac. You've never seen it before. So when you combine MRI, which gives you these really good anatomy images, with nuclear medicine, which gives you really good physiology images, you get the fused image. But this isn't what we do here. This drug right here very specifically is. We're going to do carbon 11 PBr28, which is going to measure transport proteins. This is what Channel 25 News did an article on just the other day on one of the studies that we did with this drug. We're going to do C11 raclopride, which we can make a D2 dopamine receptors. We're going to do T807 and PIB, which is where we're going to measure tau neurofibrillary bundles and beta amyloid plaque deposits, not just in Alzheimer's, but in also things like CTE, copper 64 FBP8. We're not always creative. Fibrinogen binding protein number 8, and CBP8, collagen binding protein number 8. And then clearly this has got to be my favorite. And I don't know if everyone here knows this, but there's a drug out there that we're going to use to measure, let me make sure I get this right, the histine deacetylase inhibitor, which is part of your epigenetic code. And the name of that drug is Martinos. We actually have a drug named after the work that we're doing here in this building. So why do we actually make these drugs here instead of like buy them from someone else? Well, the half-life of carbon is about 20 minutes. And then we have injection limits based on specific activity. Sometimes we actually go to the nuclear techs and say, sorry about this, you have 8 minutes to get it in the patient. It actually happens. Sometimes the expiration time on these drugs is literally less than 15 minutes. So that's why we have a cyclotron. We know how to do alchemy with the cyclotron. So here's the fun part, which is where did this whole idea come from? This journal. So what we have is we've got Ernst Lawrence. He was sitting in a meeting in 1932, and the best way to say it is it was a meeting that probably should have been an email. It was as boring as it gets. He starts flipping through this journal right here. Now, Ernst Lawrence, like most Americans, only speaks one language, and it wasn't German. That's how boring the meeting was. He's doing the math. And he says, hey, I've got an idea on how to improve this idea of this cyclotron. So he went out and did it. Now, here's the thing to remember with what he went out and did it. And like maybe if you remember most everything from this thing right there is the first cyclotron ever built. Not that complicated. It's kind of technical, but that's the very first cyclotron ever built. This won the Nobel Prize in 1939. And the moral of the story, at least from the very end part, is don't ask permission to be awesome. Just do it. If Ernst Lawrence read the German and knew that he couldn't make this work, he may have never tried it. And as always, if you want any radioactive cyanide, we can make it for you. That's my talk. I'll be around if you have any questions.